So in this video, we're going to look at conducting one sample hypothesis tests. Now, this is going to cover three different types of scenarios. So we have a z-test, a t-test, and a one proportion z-test. So in our stats menu under the tests submenu, we have z-test is the first one, t-test is the second one, and one prop z-test is number 5. Now, again, just as I've noted in the confidence interval video, the z-test is actually a very uncommon scenario. It is typically taught first because of our familiarity with the normal distribution, but it actually has very restrictive circumstances when we can actually use it. So we need to know what the population standard deviation is, and the sample size has to be very large. Typically, most of the time, either we have a small sample or the standard deviation is unknown, in which case we should resort to the t-test, just as a general matter. The t-test counts for a little bit more variability since we're making estimates from an estimate, and smaller sample sizes have more variability also. And so the t-test just does a better job of capturing that. We will walk through the z-test, but just to be aware, don't default to the z-test, default to the t-test for mean questions. And then we'll also look at the proportion test. Now, let's look at some examples. In this first example, we're going to look at the z-test, where the mean is available and the sigma is known. The standard deviation for the population is known. Again, this tends to be limited to places where we can actually obtain the population standard deviation, or where extremely large sample sizes have been conducted in order to get a really, really good estimate for them. So again, these are somewhat uncommon. But let's continue. USA Today reported that automobile plants in the United States require an average of 24.9 hours to assemble a new car. In order to reduce inventory costs, a new just-in-time parts availability has been introduced on the assembly line. Suppose that a random selection of 49 cars showed a sample mean time under the new system was 24.6 hours. Assume the population standard deviation is 1.6 hours. Does this information indicate that the population mean assembly time is different under the new system? And in this case, we're conducting a hypothesis test, and so alpha has been specified at 0.02, so we should need to keep that in mind. That's a little lower than the 0.05 we typically use. So we're going to set up our hypothesis test. The null hypothesis is going to be the old hours of assembly time, and we're going to see if the new system has changed that population. So they're asking for different, and so that's not equal to. Now, since the population standard deviation is known, or at least it's claimed to be known, we can use the z-test. So again, under the stats menu, we're going to select from the tests submenu that first one, z-test. So hit enter when you get to that. And then we're going to enter the statistics from our data. So mu naught, that's the default population for the null hypothesis. So that's 24.9. The sigma, and again, notice the notation, this is not S. The sigma was specified in the problem as 1.6. X bar was our sample mean, 24.6. The sample size was specified to be 49. And then at the bottom here, we're going to select our inequality. So in this case, the not equals to sign. If we were doing a less than, we would select this one. If we were doing a greater than, we would select this one. And then when we're done, we scroll down to calculate. We could do draw. Draw will show a distribution graph, and it will give sort of the main results. But calculate generally will give us a little bit more calculated information. So scroll down to calculate and hit enter. And then what will come up on the screen will be this information. So it will restate the alternative hypothesis. It will give us the z statistic that it calculated. it will convert that to a p-value, and then it will restate the sample mean and population. Now, the p-value here is 0.189. This is much larger than the 0.02 that was specified for alpha, and so therefore we will fail to reject the null hypothesis and conclude there is not sufficient evidence to suggest that the mean assembly time is different under the new system. Now, again, we can also look at the t-test case. Now, for the t-test, you may be given data or you may be given summary statistics. So similarly to the confidence interval scenarios, but you will notice in the problem that they either don't provide you the standard deviation or they don't specify that it's a population standard deviation. Here, they didn't specify either the mean or the population standard deviation because they just gave us the data. So, and also you'll notice that the sample size is extremely small. It is not over 30 or 40. And so therefore we should use the t-interval, the t-test anyway. So let X be a random variable that represents blood cell count in millions per cubic millimeter of whole blood. Suppose the distribution is approximately normal for the population of healthy adult females. The average RBC is 4.8. Suppose the doctor has recorded the following RBC for 6 female patients, blah, blah, blah. Here's our data. And what we want to know is, does the data indicate that the population mean RBC is lower than 4.8? And here we're going to use alpha as 0.1. Now, again, there was no specification of the standard deviation and the sample size is small. So we're going to use the t-test. We're going to set up our hypothesis statements. So we're going to say that the mean is equal to 4.8, which is the older value. And we want to see if the population data that the sample data we collected indicates that the RBC is actually lower than that. So this would be a less than. So we're going to enter the data in list 1. Again, I have another video on entering data into the lists if you don't know how to do that. And then once the data is entered into the list, you're going to go back to the stat menu and then scroll down to line 2, which is the t-test from the tests submenu. And then once we're in there, we can enter the data that was provided to us. So using data, we'll specify the default mean that we're comparing it to, the null hypothesis mean of 4.8. We'll specify the list where the data that we collected from our sample is located. The frequency should remain 1 unless we have provided additional frequency information. And then we have 3 options for the alternative, not equal to, less than, or greater than. Select the less than case, and then scroll down to calculate, and you will get this information on the screen. Now, it will restate the alternative. We're testing if the mean is less than 4.8. The t-test that was calculated will be displayed, -3.9, which is quite high. That's good. The p-value is 0.005. That is lower than our alpha of 0.01. And then it will also restate, or it also give us the mean and the standard deviation calculated from the sample. Now, since the p-value is much less than the significance level, we can reject the null hypothesis, and that suggests there is sufficient evidence from this data to suggest that this patient's RBC is less than 4.8. And then our final example is conducting a hypothesis test for the population proportion. Now, again, one good way to recognize a proportion problem is that they don't ever mention standard deviation, and they usually don't give you raw data. Proportion problems tend to need larger sample sizes to be very accurate. And so it's much easier to say, I have 600 people and 530 of them said yes or whatever. So they won't mention the standard deviation. And so that will be an indication also that you might be dealing with the population proportion. If you have a percentage statement in your problem, but they also mention a standard deviation, that's probably a means question. and you should think about the two previous examples. But let's go through this example. An instructor claims that only 60% of students ask questions when they have them. Suppose that 30 out of 45 randomly selected students reported that they ask questions when they have them. Does this suggest that the proportion is higher than the instructor claims? Use a 0.03 level of significance. So again, we should state our hypotheses. Here, the proportion is believed to be 0.6, so that's our null hypothesis. And we want to determine if, in fact, the proportion is higher based on our data. So since we're testing a population proportion, we're going to scroll down to 5, which is our one prop Z test, from the tests menu submenu in the stats menu. So hit stats, scroll over to tests, and then scroll down to 5, or just press 5, and it will take you there. The input screen is here. Notice there's no options for data or statistics. It's always summary statistics. You need to report the number of successes. So in this case, they told you that there was 30 out of 45. So they just gave you the number. And so you can just put 30 in here. If they gave you a proportion, you would multiply the proportion by the sample size and then make sure that it's a whole number. Because it won't work if it's a decimal. And then the sample size is n, that's 45. We've set the null hypothesis to be 0.6, that's what we're comparing it to. And we want to check if it's greater than. So on the 3 options we have for the hypothesis test, we select greater than, and then finally scroll down to calculate and run that, hit enter, and you will get this result. Notice again a restatement of the alternative, the z-score that was obtained, the p-value that was obtained, and then it'll restate the proportion and the sample size. Here our p-value is 0.18, which is much larger than our significance level of 0.03, and so we will fail to reject the null because the p-value is too high. So this would suggest this is not enough evidence to conclude that the proportion is higher than 60%. Even though the sample proportion is higher than 60%, the sample size was not enough to rule out that this was due to just random chance.